Hello and welcome back to Piping Design Simplified. I'm Lopamudra Satpathy, your host, and this is the third installment in our 90-day series on piping fundamentals. Today, we are diving deep into some foundational elements that are crucial for any piping engineer or designer. Understanding units, the overarching design philosophy, the critical role of data, and the art of making sound engineering assumptions. These are not just theoretical concepts, they are the bedrock upon which safe and efficient piping systems are built. So let us start with units. Sounds basic, right? But the consistent and correct application of units is paramount. A simple error in units can lead to catastrophic failures. Remember the Mars Climate Orbiter, a unit conversion error costing hundreds of millions of dollars and a mission. In piping, it can mean a ruptured pipe, a dangerous leak, or worse. Globally, we primarily operate with two major systems: the SI unit, International System of Units, and the Imperial System, which is also called as US Customary Units. SI is widely adopted, especially in new projects and international collaborations, while Imperial units are still prevalent in certain regions, particularly in North America. It is vital to know which system your project follows. All calculations, specifications, and drawings must adhere to the specified unit system. So mixing them without proper conversion is a recipe for disaster. You might encounter megapascals MPa in SI and pounds per square inch PSI in Imperial. In piping design, 1 megapascal is equivalent to 145.038 psi. So always specify if the pressure is gauge or absolute. In temperature, we do the conversion follows the formula temperature in Fahrenheit equals temperature in centigrade times 1.8 plus 32. And this is a very critical formula for calculation of thermal expansion. While most international projects use mm for dimensions, pipe sizes are often still referred to by their NPS, nominal pipe size, in inches, or DN, diameter nominal, in mm. For liquid services, GPM or gallon per minute is the standard in USA, while BPD, barrels per day, is common in upstream oil and gas. For gas, we might encounter normal cubic meter versus standard cubic feet per day. ASME B31.3 generally provides us equations which are dimensionally consistent, but always verify the specific constants used in the code when switching between unit systems. So our governing codes and standards such as B31.3 for process piping will often provide equations and data in both unit system or specify which system to use. For example, when you refer to material properties in ASTM standard, ensure you are extracting data consistent with your project in unit system. So it is advisable to clarify the project's default unit system at the very beginning. This is usually specified in the project design basis or project specification. Next, let us talk about design. Piping design is far more than just connecting points on a drawing. It embodies a comprehensive philosophy. that prioritizes several key aspects, all while adhering to stringent codes and client requirements. We have four different pillars: safety, operability, maintainability, and cost effectiveness. The absolute primary concern is safety. Every decision, every design decision, from material selection to pipe routing, must ensure the safe containment of fluids, protection of personnel, and prevention of environmental hazards. So this is explicitly stated in codes like B31.3, which aims to provide rules for the safe design and construction of power piping. Secondly, operability. Can the plant run efficiently with this piping layout? It should be the question. Does it allow for smooth process flow? Are critical valves and instruments accessible to operators? In our third pillar point, maintainability, we have certain questions like, can equipment be easily isolated, inspected, or repaired? So think about space for flange removal, valve packing replacement, or instrument calibration. Accessibility for maintenance personnel is very crucial, very important. As a fourth pillar, cost effectiveness does not mean cutting corners on safety. It means optimizing material selection, minimizing pipe runs where possible, and considering fabrication and installation cost without compromising on the other pillars. Do you have this question? Is the code compliance negotiable? Code compliance is always non-negotiable. This is the Bible. ASME B31 series codes are our Bibles. B31.1 for power piping, B31.3 for process piping, B31.4 liquid transportation, B31.8 gas transmission. We also rely on other different standards like API for specific equipments like pumps. API 610 we use for pumps. For valves, API 600 or API 60. Hence, the design philosophy permeates every stage from conceptual layout to detailed isometric drawings. It is about designing a system that meets its functional requirement, safety, reliability, and economically over its intended lifespan. This is the third section of this presentation, the foundation of data in piping design. So, is the data important? Yes. In piping design, data is our raw material. Accurate, up-to-date, and consistent data is critical. It's vital. Without it, even the best design philosophy falls apart. What are our primary source for process information? First one is PNID, piping and instrumentation diagram. This schematic shows the process flow, major equipment, instrumentation, and crucially provides the line numbers. These line numbers which are linked to our line list. Our second source is the line list. The line list is a spreadsheet detailing every pipeline in the plant, which provides critical information like service, design pressure, design temperature, fluid properties, and assigned material class. Third point is equipment data sheets. So for pump, vessel, heat exchanger, compressor, we have different equipment data sheets. And these data sheets give us essential details like nozzle sizes, ratings, orientations, dimensions, and weights. These directly impact our piping connections and support design. Our fourth source are plot plans and layout drawings. These establish the spatial constraints, equipment locations, and overall footprint of the facility. And of course, finally, material specification. These are for pipes, fittings, valves, bolts, and gaskets, which are defined based on the service conditions and codes. This ensures material compatibility and structural integrity. The integrity of this data is paramount. We constantly cross-reference between PNIDs, line list, and equipment data sheets. Any discrepancy must be highlighted and resolved. So, change management is also vital and critical. Revisions to PNIDs or equipment data must be propagated throughout the piping design. So always query the data which seems incorrect or inconsistent. It is better to ask questions upfront than to design based on faulty information. Finally, let us discuss design engineering assumptions. In any project, especially during early phases, complete and validated data is not always available. So this is where sound engineering assumptions come into play. So here is my question. When the necessary assumptions will be made? When initial project data is preliminary or incomplete. Specific vendor data is not yet available. I can give you an example. Suppose you don't have enough information about your pump dimensions. Minor details would consume disproportionate engineering effort to obtain, but a reasonable estimation is sufficient for the current stage. For instance, in the early stages, you might assume a standard flange rating of 150 for a particular line. If the exact design pressure has not been finalized but is expected to be well within that rating. There are strict principles for making assumptions. Number 1. Always err on the side of safety and over design rather than under design. That means be conservative. If you assume a pipe rack width, assume slightly larger to accommodate future unknown lines. My second principle is every assumption, its basis, its potential impact, and by whom it was approved should be documented. So it must be documented in an engineering assumptions register or similar document. This is very crucial for traceability and future verification. Our third principle is validate. What does it mean? As actual data become available, assumptions must be validated and updated. An assumption is a placeholder, not a permanent solution. Fourth principle is major assumptions should always be discussed and approved by the lead engineer, client, or relevant stakeholders. So, never make an assumption that compromises safety or code compliance. When in doubt, always ask your lead engineer or client for clarification.